There are two fundamentally different approaches to implant gas delivery design: cylinders that contain high pressure and ATMI's unique adsorbent technology that stores toxic gas subatmospherically. With conventional high-pressure cylinders, a single failure can lead to a catastrophic event. Although improvements to safety were made with high-pressure mechanical cylinders, there are a multitude of release scenarios that can occur. Some mechanical failures result in relatively small leaks and pose various risk levels to personnel, while a full catastrophic release cannot be completely eliminated. At the catastrophic end of the spectrum, a neck leak, cylinder puncture, or valve shear are the most severe that can result in a full release to atmosphere. Other failure modes can go undetected and cause internal leaks, which result in high pressure at the cylinder valve outlet, placing operators at higher risks unknown to them. Three other potential failures don't result in exposure but can result in a loss of flow and impact the implant process and reduce productivity. SDS is in a class by itself, delivering the highest level of protection against the possibility of catastrophic releases, or even various smaller leak scenarios caused by mechanical failures. It does not rely on mechanical components nor high pressure to function. Its unique carbon adsorbent technology holds the toxic gases in place via van der Waals forces and requires a vacuum to release it from its grip. With similar costs of ownership, why ever take on additional risks attributable to high-pressure mechanical delivery systems? Given the dramatically different risk profiles, regulatory bodies are classifying the adsorbent-based subatmospheric gas systems, SAGs, differently from the high-pressure mechanical type. Both the National Fire Protection Association 318 standard and the International Fire Code have made changes to their requirements differentiating SDS as lower risk versus high-pressure mechanical systems. This trend is expected to continue into the future, further lowering the cost of ownership to SDS end users. There are several realistic failure scenarios with high-pressure systems that may lead to a release. These scenarios are inherent to the fundamental concept and mechanical design of high-pressure systems. In this first scenario, the effects of a poppet failing in the open position are investigated for high-pressure mechanical arsine cylinders. If this occurs, high pressure fills to the cylinder valve. With the cylinder in an unexpected high-pressure state, a subsequent installation failure can lead to a large initial burst of liters per minute of toxic gas. Although lasting for a relatively short duration, the concentrations associated with this release can be extremely hazardous to fab personnel. In fact, during the first moments of the release, the arsine concentration levels can exceed lethal levels. Another possible scenario occurs when the regulator weld fails and allows the toxic gas to bypass all mechanical safety components. Because this is an internal failure, high pressure at the outlet would be unexpected. In this case, a subsequent installation failure could lead to a sustained release rate of approximately 6 liters per minute of arsine and up to 37 liters per minute of BF3. This real test shows a valve open release scenario of BF3, comparing the release of a high-pressure cylinder to absorbent-based SDS. The video depicts how quickly toxic gases can permeate a confined area. Only 3 grams of toxic BF3 is released in the high-pressure cylinder case and quickly fills the confined space. A new cylinder would contain over 1,100 grams. Even with the comprehensive safety systems and procedures in place, accidents do happen that are unpredictable and difficult to control. Earthquakes and fires are prime examples. In 2005, a fire broke out in a clean room at the University of Southampton. Both high-pressure and SDS cylinders were engulfed by the fire. The SDS cylinders survived intact, while the HP cylinders exploded, exacerbating clean room equipment damage and endangering emergency response personnel.